So, welcome back, and for those of you who are just joining in, we are in Chapter 16 of Bio 211 at Norwalk Community College, and what I'm doing now is I'm moving from adaptation of sensory receptors to what is actual somatic sensation. And imagine somebody just walks up to you right now and just flicks the side of your arm. There are sensory receptors that are cutaneous, that could be found inside muscles, could be found inside tendons and joints, and they're also within your inner ear. But what happens, of course, is what Mother Nature actually has to do here. She creates an uneven distribution of receptors and types of sensation that can be collected so that you end up creating four modalities. It's either tactile, thermal, pain, and proprioceptive. And even if you're asleep, there's some level of each of these that are traveling to the cortex of your brain. The reason why I said you're asleep, of course, is that you are primarily responding to subconscious stimuli, meaning you have not moved far enough up the reticular activating formation inside the brain to make you aware of them. However, the sensations have still traveled into your nervous system. And you've seen this figure multiple times in this class. In fact, the moment you finish the introductory material, we bring you here, right? Because I need you to understand that you are a sensory organism. And here are the nociceptors that are free nerve endings. And you can have Merkel or tactile discs, which are type 1 cutaneous mechanoreceptors. And here's corpuscles of touch. And when you're studying this, your responsibility is to go and don't just memorize the name. When you're reading the book, yes, reading the book, you are looking at, where do I find them? Remember, these are unevenly distributed throughout the body. Why do you have hair root plexuses where they are? Okay, obviously, because anywhere there's hair, you now have an extension of a receptor. So anytime there's a force that actually hits, let's see if I can do this without mucking it up. If there's a force that hits any follicle of hair inside your body, think of it as an alarm system. Okay, now you actually have something that's outside of the body, literally away from the surface of the skin, and has now told your body, hey, you might want to pay attention to this. Likewise, as you travel inward, you can see these Pacinian corpuscles down here. Nothing new. Those Mesner corpuscles, we don't tend to speak about them a lot, but I want you to understand, just like the corpuscles of touch, they're rapidly adapting receptors, okay, and they're found in the dermal papilla of hairless skin. And the reason why I'm pointing this out to you is like, now you should be asking yourself, where do I have hairless skin on my body? Okay? And if that's the case, now you've begun to understand what I mean by discriminating where the receptors could be, and then what those receptors are collecting in terms of unique types of information. And now we can actually get into the nervous system itself. But before we get there, let's think about some more sensations. There are two types of free nerve endings that can detect temperature change. There are cold receptors and warmth receptors. And remember, what I would like you to think about is, if you're thinking about thermal sensations, that means that you actually have an excitation. So if some things are cold, you have less sensation. Something is warm, the receptors are activated because of the increasing free energy inside of a space. Pain sensations, well, obviously these are protective. Nobody's going to tell you that pain is a pleasant thing, right? Well, you move away from it is ultimately the goal. Okay? So you have sensory receptors that are nociceptors, and these are free nerve endings, and they have types of pain which are both fast and slow. And fast pain can be acute, sharp, and or prickling pain. So that's another piece of information. Where do you actually have sensory receptors for nociceptors? Skin. Are they evenly distributed? No. Okay? You can have fast and slow types of pain being collected into them, though, where if fast would be acute, sharp, and prickling, versus slow pain, which is chronic burning, aching, and throbbing pain. And these would be the descriptors for us instructors writing test questions, for you students to determine, do you understand that pain actually comes in two types? Okay. Your textbook takes a bit of a diversion here, and it's useful if and only if you are not distracted by it, right? I don't want you walking out of this class going, well, I know where the liver and gallbladder redistribute referred pain inside my body, and that's going to make me an awesome human being. Now, it may make you a better clinician, but ultimately, at the end of the day, you are looking to increase your observation skills anyway. So that's what this is actually useful for. Someday somebody might be complaining to you, I've had this referred pain, or I have this pain just above my, I don't know, let's go right above my stomach. Okay, right here. So if my stomach's here, right, and it's been referred up here all the time, well, maybe it is actually the stomach, or it could be something else. Okay, you ask then the refining question, is it to the right of the body or to the left of the body? If it's to the left of the body, you might think pancreas. If it's to the right of the body, you might think liver, gallbladder, stomach. Okay, there's a reason for all of these things. Over time, generally speaking, this pattern tells a set of observations that might be useful to you, and we'll leave it at that in this class. Okay. What I tend to think about as the more difficult information for people is, unless you've been a gymnast or a figure skater or something where you actually have to utilize proprioceptive sensations regularly. You did martial arts for X number of years. You know exactly how much weight to place on your legs to jump a specific height. These are slow adaptation signals that utilize proprioceptors. And remember, I've said these multiple times. You find them inside muscle, tendons that are made up of connective tissue that's surrounded muscle, as well as receptors inside of the joint, of every joint inside your body. Now, stop and think about that. Hold your right hand out in front of you. Turn the palm towards your face. Now, bend each of your fingers and thumb inside towards, they move towards the palm. Now let all the fingers touch, apply a certain amount of force. Now open them up. Every single one of the joints in your fingers and thumb now collected that type of information from muscles, tendon organs, as well as the joints. So all three types of information are traveling now up to the brain. And when you started pushing on the individual fingers, you could feel the force. So your brain needs to figure out what's going on there. Let's think about what's actually happening inside the muscle spindles. So all the muscles, and I noticed I had you pull your fingers together. Interspersed amongst skeletal muscle tissue, which we haven't covered yet inside this class, but we will. It consists of two types: intrafusal muscle fibers. Okay, notice I'm going to highlight this for you. That might mean something to you. Okay. With sensory nerve endings and motor neurons called gamma motor neurons. Okay, so we have sensation traveling in, motor traveling out. You're going to notice when you look at the fibers, the color codes are opposite than what you're used to seeing. You should pay attention to that. As well as extrafusal muscle fibers that are surrounding muscle fibers supplied by alpha motor neurons. And so let's take a look at what that actually means. In this figure from your textbook, you actually have a biceps muscle where if we open up the muscle inside, I mean literally take apart the muscle, look inside here, you actually have sensory neurons, and they have pointed to them to you here. You can actually see the one on the inside. These are intrafusal muscle fibers, and they're surrounded by these structures. In red, you have a gamma motor neuron, which is actually releasing acetylcholine to cause muscle contraction. Okay? And outside here, you have alpha motor neurons that are causing extrafusal muscle fibers to contract. So what you're learning is that you have multiple ways to respond to stimuli that are collected by muscle itself. Okay, so if you actually push on a muscle, it can cause muscle contraction. How can that happen? Well, the body will respond to the actual intrafusal muscle fibers here being stretched. Also over here, we have our tendon organ capsule. Golgi tendon organ capsule. It's collecting sensory information as well. So if you're pulling on this and the information matches up with the sensory input pulling from here, then your body knows you're actually activating, shortening the distance between the 2 points. Here's A, here's B. You're actually causing a muscle contraction. They're designed, those Golgi tendon organs are designed to protect as a result of excess tension. So think about the last time you went to the gym and you lifted up a 150-pound barbell or dumbbell and you tried to curl it. Now, maybe some people inside the classroom could do that. I know I can't. If I didn't, I'd probably rip the tendons and the muscles off of the bone. Okay? Your body stops you from doing that. Those joint kinesthetic receptors, they're found inside the articular capsule of joints inside the body. And maybe you know what a synovial joint is, but if you don't worry about it. We'll then also use Ruffini corpuscles as well as Pacinian corpuscles that are going to respond to acceleration and deceleration of joint movement. So your body knows when you're moving your arms and knees and hips faster as you're sprinting. So the last part, I should say the last two pieces here, I'm going to introduce this and we're going to stop and we'll start all over again. But from AMP1, from essentially the very first day of class, what I've been trying to do is make sure you guys understand that you are a sensing system that will have a series of mechanisms that will then get information to the brain so you can think, make decisions, act, right? Okay. Having said that, here's our first order, our second order, and our third order neuron. And inside class, I've been drawing these things here, okay, where you always know that first order neuron is a myelinated unipolar neuron. All hell breaks loose when you start tearing apart what's actually going on inside the pathways. So this is why we collectively just call these guys interneurons. Okay? So that's what we're talking about here. So this should make sense to people who have been in the class. If you're reading your textbook or if you're inside a different class, maybe you're in medical school or something, this is what they're talking about. And they're going to go through the different pathways to make sure you actually can see them. What's going to happen, of course, that first order neuron will collect the information. It's going to send it to that second order neuron where it's going to travel to the thalamus and it will decussate before it gets there. Okay, and the third order neuron will then send that information from the thalamus to the primary somatosensory area of the cortex. Big fancy way of saying post-central gyrus. So let's put that in there. Post-central gyrus. And every textbook explains it a slightly different way, meaning they use vocabulary in a different order, but they all mean the same thing. Okay? Doesn't matter. Go to Harvard Medical School, you look at their slides, they're going to tell you exactly the same thing. They're going to go into a little bit more painful detail than we are right now, but that doesn't mean they're learning something that you're not. Okay. So how are we going to do this? There are major somatic sensory pathways. There's a posterior column medial lemniscus pathway. What I can tell you is this, is you have to learn what each word means. And the moment you've done that, you've figured out what the pathway is. Same thing with the anterolateral or spinalphilemonic. Spine goes to thalamus. Anterolateral, anterior and lateral pathways. Trigeminalthalamic pathway. Trigeminal cranial nerve, possibly. Thalamic going to the thalamus pathway. As well as anterior and posterior spino-cerebellar. Okay, well, cerebellum is balance and coordination. So maybe we might want to think about what that's going to do. Let's go through this. Posterior column medial lemniscus pathway. That is something you could impress nobody with at a bar. Remember, what I want you to do here is take a look at how do you decide what pathway are you on. You ask a series of questions. Am I detecting touch, pressure, vibration? Okay. And where am I detecting it from? Is it the limbs, trunk, neck, posterior head that will ultimately end up going to the cerebral cortex? And what do I mean by that? Take a look down here. Your textbook just uses, say, the lumbar spinal cord. Well, it says for lower limbs and lower trunk. We collect this here, and what you're going to do is follow that blue line up, and you're going to see you actually travel through the gracial fasciculus. You travel up in the gracial nucleus. You decuss. You travel up to the medial lemniscus. Notice what we've done was crossed over the midline of the brain. And now you're midline of the body to actually ascend to the brain, and now we're going from our thalamus to our cortex. Okay? Now, if we're collecting information of touch, pressure, vibration, and proprioception in the upper limbs, upper trunk, neck, and posterior to the head, it still travels in as a unipolar neuron. It ascends now through the cuneate fasciculus. It travels to the cuneate nucleus. It decusses here inside the medulla, travels to the thalamus, and then goes to its location inside the cortex, depending on the type of the information it's carrying. Is it touch, pressure, vibration, and proprioception? Okay. Once you get the handle of it, hopefully what you're going to do is just ask yourself a series of questions. How do I know what type of information is being collected? And if I do know that, which pathways do I remember can get it to the actual cortex? Let's use another example. Spinalphilemon Pathway. Okay, well, look at here. We're going directly from the spine, we'll call them, where our first order neuron activates our second order neuron inside the posterior gray horn. We haven't seen that before. It decusses through either the gray matter or the white matter, and then ascends to the medulla, directly to the thalamus, directly to the cerebral cortex. Notice what it's carrying. it's carrying pain, cold, warmth, itch, and tickle from the limbs, trunk, and neck, as well as the posterior head, and it's taking all of that to the cerebral cortex. So draw a stick man. Put these types of sensation from the limbs, the trunk, and the neck, as well as the posterior head. And that's how you get this type of sensation, pain, cold, warmth, tickle, and itch, up to the cortex of the brain. One more before we switch over to muscle, okay? Trigeminalthalamic. Notice it's going to be receptors for touch, pressure, vibration, cold, warmth, itch, tickle, in the face, nasal cavity, oral cavity, and teeth. So a little bit more detail here. And you're going to see that it's coming in on the trigeminal nerve, which is number 5, right? First order neuron. And then one of two things can happen. It stays in the pons, or it drops down to the medulla, where it will decuss there. So in the trigeminalthalamic pathway, we have 2 sites of decussation. They both end up ascending to the thalamus, and they both end up traveling to that primary somatosensory cortex. Okay? So to review these 3, which we'll do during the review of your exam, right? What I want you to pay attention to is when we're writing these exam questions, we're like, well, you know, if we're getting somatic sensations from the face, nasal cavity, oral cavity, and teeth, it has to go to the cerebral cortex. What type of information is going to have to travel on it? Okay, so I'm going to back up. I'm going to stop here, okay? And I'm going to make the last set of slides for chapter 16. So this will be part B, and there'll be finally part C, where I'm going to go over the somatosensory pathway again, and we'll work our way through the mode or pathways. Okay, see you in a bit.